Gaze out into the depths of space, and you'll see it, a magnificent swirl of color and energy, a cosmic masterpiece known as the Crab Nebula. To the naked eye, it might look like just another cloud of stardust, but what if I told you this breathtaking nebula holds secrets that defy our very understanding of physics? What if the beautiful, tranquil scene you're seeing is actually a stellar graveyard, filled with mysteries that leave even the most brilliant astronomers utterly baffled? At the heart of this nebula lies something extraordinary, a pulsar, spinning faster than a kitchen blender, shooting out beams of radiation like a cosmic lighthouse. This isn't just a dead star, it's a powerhouse of energy, a celestial phenomenon that challenges everything we think we know about how the universe works. And the strangeness doesn't stop there. This pulsar and the nebula surrounding it are home to events so bizarre, so utterly unexplainable, that scientists are still scrambling to make sense of them. From mysterious gamma-ray flares that appear out of nowhere to energetic particles moving faster than should be possible, the Crab Nebula is a place where the rules of physics seem to break down right before our eyes. So join me on a journey into one of the most fascinating corners of our universe as we uncover 30 of the strangest, most mind-bending phenomena hidden within the Crab Nebula. This is more than a tour of cosmic wonders, it's an exploration of the very limits of human knowledge, a chance to witness the unanswered questions that keep astronomers up at night. You're about to see the universe in a whole new light, and I promise by the end, you'll never look at the night sky the same way again. Our first mystery brings us to the very heart of the nebula itself. Nestled within that beautiful cloud of gas is a cosmic powerhouse, an object of such immense density and ferocious energy that it defies our expectations at every turn. This is the Crab Pulsar, and its most baffling feature is its seemingly eternal spin. This neutron star, the collapsed core of that famous supernova observed in 1054, is a celestial zombie. It's dead, yet it's impossibly active. It rotates a staggering 30 times every single second. Now, to put that into perspective, imagine a sphere more massive than our sun, compressed into a city-sized ball, spinning faster than the blade of a kitchen blender. It's a dizzying, almost incomprehensible speed. The real puzzle, however, isn't just its current spin. It's the fact that it's still spinning this fast after nearly 1,000 years. According to all our established models of physics, a neutron star like this should be slowing down dramatically over time. As it spins, it acts like a colossal dynamo, converting its own rotational energy into the powerful winds and radiation that illuminate the entire nebula around it. This process should act as a powerful brake, steadily reducing its spin. Think of it like a spinning ice skater who extends their arms to slow down. The pulsar is constantly extending its energy out into space, and it should be slowing to a crawl. But the Crab Pulsar isn't slowing down nearly as much as it should be. It's holding onto its rotational energy with a tenacity that has left astrophysicists completely stumped. It's as if that ice skater simply refuses to slow down, defying the fundamental laws of friction and energy loss. So what could possibly be keeping this cosmic top spinning? Scientists are forced to consider explanations that sound like they're ripped from the pages of a science fiction novel. Some theories propose the existence of exotic states of matter in its unfathomably dense core, a superfluid soup of subatomic particles that swirls with minimal friction, providing an internal energy source that we can't yet fully comprehend. Other ideas point to complex behaviors within the star's superfluid interior, like the formation of quantum vortices. These are tiny, swirling tornadoes of energy that could be transferring momentum in ways that counteract the braking effect. It's a celestial balancing act of unimaginable scale and complexity. This pulsar isn't just a dead star. It's a natural laboratory testing the very limits of quantum mechanics and nuclear physics under conditions we could never hope to recreate on Earth. Its relentless, immortal spin is our first clue that the Crab Nebula operates by a set of rules we are only just beginning to glimpse. Yet for all its steady rhythm, the Crab Pulsar harbors a violent, unpredictable temper. The next baffling phenomenon rips through the nebula without warning, an event of such staggering ferocity that it rewrites the rules of stellar energy right before our instruments. These are the gamma-ray superflares. Picture the Sun, our local star, a constant and reliable furnace bathing our solar system in light and warmth for billions of years. Now imagine an explosion that, in a fraction of a single second, unleashes more energy than our Sun will emit over an entire year. This isn't science fiction, it's a documented reality in the Crab Nebula. These flares are so intensely bright that they briefly outshine every other persistent source of high-energy light in the entire sky, including the pulsar's own steady beacon. The sheer scale of these outbursts is what catapults them from mere curiosity to full-blown cosmic conundrum. Our current understanding of pulsar physics centers on the incredible magnetic field and rapid spin of the neutron star, which act together like a massive, highly organized generator. This model beautifully explains the pulsar's steady, clockwork tick of radiation. But these superflares are anything but orderly. They are chaotic, explosive tantrums that seem to come from nowhere, suggesting a complete and instantaneous breakdown of that organized system. It's as if a perfectly designed power plant suddenly, for a millisecond, released the total energy output of 100,000 suns before returning to normal operation as if nothing happened. The mechanism behind this is utterly unknown, forcing scientists to consider processes of an almost apocalyptic scale happening on the surface of this city-sized star. Two leading theories attempt to grapple with this impossible power, and both sound like concepts from a theoretical physicist's wildest dreams. The first points to colossal starquakes. The neutron star's crust, a phenomenally dense lattice of atomic nuclei, is under unimaginable strain from the star's rotation and its intense magnetic field. This crust is not perfectly smooth. It can develop faults and fissures. When the stress becomes too great, this crust might suddenly crack and shift, snapping into a new configuration. The energy released in this single planet-shattering seismic event, a starquake, could be channeled through the magnetic field, triggering a massive reorganization of its lines in a process called magnetic reconnection. This event acts like a colossal slingshot, violently accelerating particles to near light speeds and producing the sudden, blinding flash of gamma rays we observe. The second theory delves even deeper into the bizarre, suggesting the flares might originate from within the star's own superfluid interior. This quantum realm, where friction almost ceases to exist, could be building up vortices of energy that suddenly and catastrophically erupt through the crust, punching their way out into the magnetosphere. Whichever process is at work, or perhaps some terrifying combination of both, these superflares stand as a humbling reminder. They show us that even in a system we think we understand, there are forces at play so powerful and so poorly understood that they can, in a literal flash, overwhelm our best models of the universe. These flares, for all their violence, illuminate a brief moment of chaos at the heart of the nebula. But other mysteries are far more subtle in their appearance, only to reveal a structure so perfect it seems almost impossible. Our next enigma trades explosive energy for geometric precision, the mysterious concentric radio rings. In a region of space defined by violent turbulence and chaotic energy, astronomers have observed something that simply shouldn't be there: perfect, ghostly circles expanding outward from the pulsar like ripples on a pond. They appear and vanish on timescales of days or weeks, detected not in visible light but in the radio portion of the spectrum, and their origin is a puzzle that challenges our basic understanding of how matter behaves in such an extreme environment. The very existence of these rings is a profound contradiction. The space around the Crab Pulsar is a maelstrom. It's filled with a hurricane of high-energy particles and tortured magnetic fields, a place where any orderly structure should be instantly shredded and torn apart by the incredible forces at play. It would be like trying to form a perfect, stable soap bubble in the middle of a Category 5 hurricane. And yet, these rings not only form, they maintain their near-perfect circular symmetry as they expand. This isn't a vague, wispy cloud. It's a defined geometric structure emerging from pure chaos, and that alone forces us to reconsider what is physically possible within a supernova remnant. So what cosmic artist is drawing these perfect circles in the sky? Scientists are investigating several fascinating possibilities, each more incredible than the last. The leading theory involves bizarre and poorly understood plasma processes. The nebula is filled with this fourth state of matter, a superheated soup of charged particles that is completely dominated by the pulsar's immense magnetic field. It's possible that sudden, powerful waves are being sent through this plasma. These wouldn't be ordinary sound waves, but something far more exotic, perhaps shocks or oscillations that cause the plasma to compress and expand in a spherical pattern. As this shell of compressed plasma expands, it could emit synchrotron radiation, lighting up briefly in radio waves to create the illusion of a ring before dissipating back into the nebula's background fury. Another, even more mind-bending idea points to the warping of space itself. The pulsar is an object of immense density, and according to Einstein's theory of general relativity, such a massive object curves the fabric of space-time around it. It's conceivable that this gravitational field could act as a lens, but not for light in the conventional sense. Instead, it might be focusing and shaping the outflow of particles and energy from the pulsar in a way we've never observed before. This gravitational lensing could potentially sculpt the turbulent wind into those temporary concentric circles. If true, it would mean we are seeing a unique and complex interaction between gravity and particle physics playing out on a scale and in a way that no model has ever predicted. The appearance of these rings is a brief, faint signal, but it speaks to a hidden order within the chaos, a set of physical laws operating in the nebula's heart that we are only just beginning to detect. Just when you thought the Crab Pulsar's behavior couldn't get any more bizarre, its most famous feature, its clockwork rhythm, occasionally breaks. This celestial metronome, which has ticked with near-perfect precision for centuries, sometimes skips a beat. Its radio pulses, the very signals that make it a pulsar, can falter, stutter, or vanish entirely for a few rotations before snapping back to their regular rhythm as if nothing happened. These events are known as nulling pulses or glitches, and while other pulsars exhibit similar behavior, the Crab does it with a flair that defies conventional explanation, suggesting a turmoil beneath the surface that we are only beginning to sense. The standard model for a pulsar is relatively straightforward. A beam of radiation powered by the star's rotation and magnetic field sweeps past Earth with each spin, creating the pulse we detect. It's a lighthouse effect, and it should be incredibly stable. So when this lighthouse suddenly winks out, even for a split second, it signals a fundamental interruption in that well-oiled machine. For the Crab, these aren't just simple hiccups. The patterns of disruption are complex and varied. Sometimes the pulse weakens noticeably, other times it shifts in its timing, and on rare occasions it disappears completely for multiple rotations. This isn't the behavior of a simple rotating magnet. It's the signature of a dynamic and perhaps deeply fractured object. One compelling theory to explain this strange heartbeat involves a phenomenon called free precession. Imagine a spinning top just as it starts to wobble. That slow, graceful circle its axis traces in the air is precession. Now apply that to a city-sized ball of nuclear matter spinning 30 times a second. If the Crab Pulsar is ever so slightly asymmetrical, perhaps due to a mountain range on its surface or a denser region within its core, it could begin to wobble as it spins. This tiny wobble would ever so slightly change the angle of its radiation beam relative to Earth. From our perspective, the pulse's strength would appear to rhythmically strengthen and weaken over time, and if the beam wobbled too far away from us, it might seem to null entirely for a beat or two. Detecting this subtle dance would be a monumental challenge, but it would provide a stunning glimpse into the pulsar's actual shape and internal structure. But what if the cause isn't a wobble but a crack? The concept of starquakes returns here with a vengeance. The pulsar's crust is under unimaginable strain, and a sudden shift, a stellar-scale tectonic event, could instantly change the star's moment of inertia. This is like an ice skater pulling their arms in suddenly to spin faster. A starquake could cause the pulsar's spin to slightly speed up or slow down in a glitch, disrupting the precise timing of its pulses. Furthermore, such a quake could temporarily reconfigure the magnetic field lines that channel the radiation beams, essentially short-circuiting the lighthouse mechanism and causing the pulse to null out until the magnetic field settles back into its stable state. Perhaps the most tantalizing, though speculative, theory involves an unseen dance partner. Could there be something else lurking in the immediate vicinity of the pulsar, gravitationally tugging at it and disturbing its rhythm? While no conventional companion star could survive the supernova that created the pulsar, astronomers have theorized about the possibility of a leftover exotic object. This could be a small, previously undetected white dwarf or even a black hole in a tight, fast orbit around the pulsar. The gravitational pull from such an object would periodically yank on the pulsar, potentially causing detectable timing anomalies and disruptions in its emission. While no clear evidence for such a companion exists yet, the sheer strangeness of the Crab Nebula means it remains a fascinating, albeit remote, possibility. Each skipped beat is not a malfunction. It's an encrypted message from the heart of the nebula, a clue about the extreme physics governing an object that should be simple but is anything but. While the pulsar's sporadic behavior and strange rings capture our attention, some of the nebula's most profound secrets are hidden in a light our eyes cannot see. To truly peer into its energetic heart, we must turn to the X-ray vision of space telescopes like Chandra. What they've revealed is a landscape of baffling contradictions, where brilliant, searingly hot spots of energy appear and vanish in ways that completely defy our expectations. These are not the predictable, steady glows we might expect from such a well-studied object. They are dynamic and mysterious phenomena that challenge the very core of our understanding of how particles are accelerated in the universe. We understand the basic engine of the nebula, the pulsar's fierce wind, a torrent of charged particles and magnetic fields, slams into the slower-moving gas of the nebula itself. This collision creates a massive shock front which acts as a powerful particle accelerator, boosting electrons to nearly the speed of light. As these ultra-relativistic electrons are whipped around by magnetic fields, they emit synchrotron radiation across the spectrum, from radio waves all the way up to X-rays. The models predict that this process should create a relatively smooth and stable distribution of X-ray light, brightest near the shock front and gradually fading as you move outward. But Chandra's exquisite vision shows us this is not the case at all. Instead, the inner nebula is a tangled, chaotic web of bright knots and rapidly changing filaments, a cosmic puzzle that refuses to fit together neatly. The most confounding aspect of these X-ray features is their sheer unpredictability. Astronomers observe specific, brilliant knots of X-ray emission that suddenly flare to incredible intensities, becoming conspicuously hot for weeks or months, only to subsequently fade away as if nothing had happened. Other regions, which should be blazing with energy, appear strangely dark and quiet. Even more puzzling is that these dramatic changes in X-rays often have no correlation whatsoever with what we see happening in other wavelengths of light. A knot might be going through a violent tantrum in X-rays, while the exact same spot in visible light or radio waves remains completely calm and unchanged. This disconnect is a major clue that the processes generating the highest energy light are operating under a completely different set of rules. isolated from the mechanisms that produce the nebula's beautiful visible glow. This bizarre behavior strikes directly at our models of particle acceleration. The standard theory suggests that particles gain their energy in a relatively steady, continuous process at the main shock front, after which they slowly diffuse outward, losing energy as they go. The wild variability of the X-ray hotspots suggests this picture is far too simple. It implies that particle acceleration is not happening in one single, stable location, but is instead a messy, fragmented process occurring in multiple, isolated sites throughout the inner nebula. Perhaps secondary shock waves are constantly forming and collapsing within the turbulent wind itself, creating temporary and powerful accelerators that give certain groups of electrons an enormous, extra kick of energy before the chaotic environment tears them apart. Another leading hypothesis points to the magnetic field itself as the culprit. The magnetic fields within the nebula are unimaginably complex and powerful. It's possible that certain regions can become tightly knotted, essentially creating magnetic traps that confine and concentrate these high-energy electrons for a time. Within these invisible cages, the particles could be forced to radiate their energy away much more efficiently, creating a temporary, brilliant hotspot in X-rays. When the magnetic knot inevitably destabilizes and relaxes, the hotspot would vanish as the particles escape. This would explain the rapid flaring and fading without leaving a trace in other wavelengths. The true mechanism remains one of the most active and challenging areas of research in high-energy astrophysics, forcing scientists to continually refine their ideas about how nature's most powerful accelerators truly work. If the Crab Nebula's X-ray hotspots represent a hidden, chaotic energy, then its most famous visual trick plays out in plain sight, creating an illusion so perfect it seems to break the universe's ultimate speed limit. Gaze at time-lapse images taken by the world's most powerful telescopes, and you'll witness something impossible. Bright, filamentary wisps of gas in the nebula's inner regions, surging outward at velocities that appear to exceed the speed of light. Some of these optical features seem to move at up to 1.5 times light speed, a feat that, if real, would overturn a cornerstone of modern physics. But this is not a flaw in our understanding of Einstein's theories. It is a magnificent cosmic magic trick, one that reveals the incredible energies and geometries at play. This phenomenon, known as superluminal motion, is a profound and dramatic illusion. The key to understanding it lies not in the actual speed of the gas, but in the speed of the light it emits and the angle at which we observe it. Imagine a distant galaxy with a jet of material shooting out from its center at nearly the speed of light, but pointed almost directly towards Earth. Now picture a single blob of matter within that jet. As that blob moves through space, it emits light continuously. The light it emits at a point closer to us has less distance to travel than the light it emitted a moment earlier from a point farther away. When the blob is moving toward us at a significant fraction of light speed, the later light can actually arrive at our telescopes almost simultaneously with, or even before, the earlier light. This compresses the time between the arrival of signals, making the object's apparent motion across the sky seem vastly faster than its real velocity. It's akin to a plane flying low over your head. The sound it creates seems to come from a point far behind its actual location because the sound waves take time to reach you. In the Crab Nebula, the magician is the pulsar wind itself. The central pulsar is firing a relentless, high-speed wind of particles outward into the surrounding nebula. This wind is not a uniform stream. It is structured and contains waves of energy or shells of concentrated particles. When these shells plow into the slower-moving outer material of the nebula, they create shock waves that heat the gas, causing it to glow brilliantly. These glowing fronts are the optical wisps we see. Now, crucially, this entire system is not static. It is a dynamic, expanding bubble. The shock fronts we observe are not solid objects moving through space, but rather patterns of energy, like the crest of a wave moving across the ocean. The material itself may not be traveling at light speed, but the wave pattern of energy transfer can propagate across our line of sight at an incredible rate. Our perspective from Earth is the final ingredient for the illusion. If this expanding shock wave is directed even slightly towards us, the same light travel time effect that explains the galactic jet comes into play. The actual physical shock wave might be moving at 90 or 95% of the speed of light, which is already mind-bogglingly fast. But when we factor in the geometry and the arrival time of the light, our calculations of its apparent motion across the plane of the sky can easily surpass light speed. We are not seeing matter itself violate relativity. We are seeing a relativistic projection, a trick of the light that only occurs under the most extreme conditions. The existence of this illusion is in itself concrete proof of the relativistic velocities at work. It confirms that the pulsar wind is indeed one of the most powerful and efficient particle accelerators in our galaxy, capable of launching patterns of energy that, from our vantage point, perform the ultimate magic act, appearing to outrun light itself. But even as we marvel at these relativistic illusions, we are forced to confront a far more fundamental mystery, one that strikes at the very core of our understanding of the Crab Nebula's power source. This is the energy paradox. For decades, astronomers have carefully measured two crucial numbers: the staggering amount of energy pouring out of the entire nebula across all wavelengths of light, and the rate at which the pulsar is slowing down as its rotational energy is converted into that very radiation. In any well-understood system, these two numbers should match. The energy lost by the spinning pulsar should be precisely equal to the energy gained by the glowing nebula. It's a basic principle of conservation of energy, the bedrock of physics, but in the Crab, the math simply doesn't add up. The nebula is shining far too brightly. The discrepancy is not a small rounding error. It is a glaring hole in our accounting of the universe's energy budget. The pulsar's spin-down energy, while immense, appears to be insufficient to power the brilliant light show we observe. It's as if we've carefully measured the fuel going into a car's engine, only to discover that the car is somehow producing twice the horsepower it should be capable of. This leaves scientists with two equally profound possibilities. Either we are missing a significant source of energy input, or there is a major, unknown mechanism of energy loss that we are failing to account for. Both options force us to consider physics that operates far beyond our current standard model. One fascinating explanation for the missing energy involves the pulsar itself emitting energy in a form we cannot easily detect: gravitational waves. According to Einstein's theory, any asymmetrical, massive object will ripple the fabric of space-time as it rotates. If the Crab Pulsar has even a tiny mountain on its surface or a slight internal deformity, an asymmetry no larger than a few centimeters on an object 20 kilometers across, its rapid rotation would make it a potent source of these ripples. Gravitational waves carry energy directly away from the system, stealing rotational energy from the pulsar without ever lighting up the nebula. This lost energy would neatly explain the gap in our calculations. While we have not yet definitively detected gravitational waves from the Crab, it remains a prime target for observatories like LIGO, as a confirmed detection would not only solve this paradox but also provide an unprecedented look inside the structure of a neutron star. An even more speculative yet thrilling possibility involves the hidden hand of dark matter. We know this mysterious, invisible substance makes up about 85% of the matter in the universe, but we have never directly observed it or know its properties. What if the dense core of the Crab Pulsar is acting as a natural trap for dark matter particles? If certain types of dark matter exist, they could be drawn to and accumulate within the incredible gravitational well of the neutron star. Once inside, these particles could annihilate with one another, converting their mass directly into pure energy in a process that would provide a powerful, hidden power source for the nebula. This energy would supplement the pulsar's spin down, making up the shortfall and resolving the paradox. It's a long shot, but the Crab Nebula's persistent refusal to follow the rules makes it a perfect natural laboratory to search for such exotic physics. This energy paradox is more than an accounting error. It is a direct challenge, compelling us to look beyond the visible and consider that the true workings of this cosmic engine may be hidden in the invisible fabric of the universe itself. Yet for all the grand illusions and energetic paradoxes, some of the nebula's most telling clues are found not in brilliant images, but in the precise rainbow-like breakdown of its light. When astronomers pass the crab's glow through a spectrograph, splitting it into its constituent colors, they are presented with a barcode of the universe, a series of bright and dark lines that act as fingerprints, revealing the exact chemical elements present and the physical conditions they endure. Most of these lines are familiar, telling the story of hydrogen, helium, and other common stellar ingredients, but a few are not. A handful of enigmatic emission lines appear in the crab's spectrum that stubbornly refuse to match the signature of any known element or molecule on the periodic table. They are spectral ghosts, and their very existence hints at physics operating in realms we have yet to fully explore. The mystery of these strange lines is profoundly fundamental. In the well-mapped world of atomic physics, every element has a specific set of energy levels its electrons can occupy. When an electron drops from a higher level to a lower one, it releases a photon of light at an extremely precise wavelength, creating a unique and predictable spectral line. For over a century, we have catalogued these lines for every element under a vast range of temperatures and pressures. The fact that the Crab Nebula emits light at wavelengths that don't correspond to any known transition is like finding a fingerprint at a crime scene that doesn't match any person on Earth. It suggests the presence of a culprit we haven't met yet, one that plays by a different set of rules. One of the most compelling explanations for these spectral ghosts points to the incredible power of the nebula's magnetic fields, which are among the strongest in the known universe. In such intense fields, the behavior of atoms is completely distorted by a process called the Zeeman effect. Normally, an electron orbiting a nucleus can be thought of as a tiny magnet, and when placed in an external magnetic field, its energy levels split into several closely spaced levels. Under the titanic magnetic stress near the Crab Pulsar, this splitting could become so extreme that it fundamentally reshapes the atom itself, creating entirely new and unfamiliar energy transitions. The spectral lines emitted from these magnetized atoms would be shifted to wavelengths we've never recorded in any laboratory on Earth, simply because we cannot hope to generate magnetic fields of such staggering magnitude. We could be seeing the light of atomic physics pushed to its absolute limit. An even more exotic theory ventures into the bizarre realm of quantum electrodynamics, or QED. This branch of physics describes how light and matter interact in extreme detail, and it predicts that in a vacuum seething with unimaginably strong magnetic fields, something truly strange can happen. The vacuum of space itself can become birefringent, a property usually associated with crystals like calcite that split light into two beams. In this QED vacuum, the magnetic field is so powerful that it affects the very quantum nature of empty space, potentially modifying how light propagates through it and creating unusual polarization effects that could masquerade as strange spectral features. While this might not directly create new emission lines, it could significantly alter existing ones in ways we don't yet understand, making them appear foreign and unrecognizable. Perhaps the most tangible, yet still mysterious, possibility involves exotic molecular ions. In the tumultuous environment of the nebula, atoms are constantly being stripped of their electrons and smashed together to form new, short-lived molecules. It's possible that under these unique conditions of density, temperature, and magnetic fury, certain molecular ions could form that are simply too unstable to exist anywhere else. These ions would have their own unique set of rotational and vibrational energy levels, producing spectral lines that have never been studied because the molecules themselves cannot be created in any terrestrial experiment. The search for these lines is not just about identifying a missing puzzle piece. It is a direct probe into the complex and violent chemistry that occurs only in the aftermath of stellar death, offering a glimpse into molecular forms that nature only permits under the most extreme duress. But the spectral mysteries only deepen the puzzles surrounding the nebula's very substance, leading us to one of the most fundamental enigmas of all, the case of the missing mass. When astronomers attempt to weigh the entire Crab Nebula, to add up all the glowing gas, dust, and energetic particles we can see, they arrive at a startlingly low number. The total visible mass amounts to only a few solar masses. This is a serious problem because the supernova of 1054 was a cataclysm of epic proportions, the death of a star that was almost certainly between 8 and 12 times more massive than our own Sun. A star that size should have left behind a remnant containing significantly more material. So where did the rest of it go? It's a cosmic accounting error on a monumental scale, suggesting that a huge portion of the original star has simply vanished without a trace. This isn't a small miscalculation, it's a gaping hole in our understanding of stellar life cycles. The leading theory for such a supernova, known as an electron capture supernova, involves a star in a very specific mass range. As such a star dies, its core becomes so dense that electrons are literally forced to merge with atomic nuclei in a sudden, catastrophic process that triggers the explosion. This model predicts that the resulting nebula should contain a specific amount of mass, and the Crab's measured weight falls short. This forces us to consider some truly radical possibilities for what became of the star's missing bulk. One compelling line of thought suggests the mass might be hiding in plain sight, but in a form we cannot easily detect. The most obvious candidate is a vast halo of cold, neutral gas and dust that has been flung so far from the explosion's epicenter that it has cooled and faded into near invisibility. Our telescopes are tuned to see the nebula's hot, energized heart, but they might be completely blind to these colder, darker outskirts. Another, more exotic idea involves the pulsar itself. Its incredible wind has been blowing for 1,000 years, a relentless stream of particles racing out into the interstellar medium. It's possible that a significant portion of the original star's mass was converted into this wind and has already traveled far beyond the visible boundary of the nebula, dissipating into the galaxy where it blends into the background. Yet these conventional explanations might not be enough to close the gap, leading scientists to ponder forces far beyond the ordinary. Could the missing mass be tied to the mysterious dark matter that permeates the cosmos? We know dark matter does not interact with light, making it completely invisible to our telescopes. If the progenitor star had an unusually high concentration of dark matter trapped within it, the supernova explosion could have scattered this unseen component far and wide, leaving no observable signature except for a glaring deficit in the total mass we can account for. While this remains highly speculative, the Crab Nebula serves as a natural laboratory where such wild ideas can be tested against cold, hard observational data. Perhaps the most mind-bending possibility of all is that a portion of the star's mass was not lost but transformed. Einstein's famous equation, E equals mc squared, tells us that mass and energy are two sides of the same coin. The supernova released an almost unimaginable amount of energy. What if the mechanisms of that explosion were even more efficient than we thought? Could some unknown physical process within that stellar collapse have directly converted a significant fraction of the star's mass into pure energy that now powers the nebula's brilliant glow and the pulsar's furious spin? This would not be a simple conversion like nuclear fusion. It would require a process of utter annihilation, something more profound that we have not yet discovered. The missing mass of the Crab Nebula is more than a puzzle. It is a direct challenge to our models of how stars live and die, pushing us to consider that the universe might have ways of making matter disappear that we are only beginning to glimpse. While the Crab Nebula presents a brilliant spectacle of light and color, the true nature of its energy can only be fully understood by examining not just the brightness, but the very direction in which that light vibrates. This property, known as polarization, acts like a hidden compass, revealing the invisible architecture of magnetic fields that thread through the cosmic cloud. For the most part, the nebula's light is highly polarized in a pattern that aligns beautifully with our standard model of synchrotron radiation. The process where electrons spiral around magnetic field lines at near light speed, emitting light that vibrates in a preferred direction perpendicular to the field. This should create a predictable, ordered map of polarization, but the crab, as always, defies expectation. Astronomers have discovered strange, localized anomalies where the polarization patterns become chaotic, twisting and changing in ways that no standard model can explain, suggesting that the magnetic fields within are far more complex and dynamic than anyone ever imagined. Imagine trying to map the wind patterns on a distant planet by watching the direction leaves blow. In most of the nebula, the leaves all swirl in an orderly, predictable fashion, indicating a smooth, global wind. But then you spot a region where the leaves are spinning in frantic, contradictory whirlpools, defying the prevailing breeze. That's what these polarization anomalies are like. In certain knots and filaments, the angle of polarization veers off sharply from its predicted path, and the degree of polarization, how strongly the light prefers one vibrational direction, can suddenly drop or surge. This isn't a gentle deviation, it's a complete breakdown of the orderly pattern, telling us that in these localized regions, the magnetic field is either incredibly tangled, rapidly changing, or being influenced by a process we haven't accounted for. One leading hypothesis to explain this chaos focuses on the violent interaction between the pulsar wind and the nebula itself. The wind isn't a smooth flow, it's likely riddled with instabilities and turbulence. As this high-speed wind rams into the slower-moving outer material, it doesn't just create a single, clean shock front. It can generate a multitude of smaller, secondary shocks and eddies. Within these turbulent regions, the magnetic field lines aren't neat and straight. They are constantly being stretched, folded, and shredded like dough in a mixer. This would create a knotted, complex magnetic environment where the field direction changes dramatically over very short distances. Electrons spiraling through this magnetic maze would emit light with a confused polarization signature, their orderly dance disrupted by the chaotic field, resulting in the anomalous patterns we detect. An even more intriguing possibility is that we are witnessing the signature of magnetic reconnection events. This is a process also seen in solar flares, where magnetic field lines of opposite polarity are forced together, suddenly breaking and reconnecting in a new configuration. This explosive event releases a tremendous amount of energy and violently rearranges the local magnetic field. If such events are happening within the Crab Nebula, they would create brief, intense hotspots of activity where the magnetic field geometry is completely reconfigured in an instant. The polarization of light from that spot would undergo a sudden, drastic shift, appearing as a sharp anomaly in our data before settling into a new, temporary pattern. The presence of these events would suggest the nebula's interior is a place of relentless magnetic violence, where fields are constantly tearing themselves apart and reforming. The most profound explanation, however, ventures beyond mere complex geometry and into the realm of new physics. Our entire understanding of synchrotron radiation is based on quantum electrodynamics operating within a classical magnetic field framework. But what if the magnetic fields in these anomalous regions are so unimaginably strong that they begin to affect the quantum vacuum itself? In such extreme conditions, the vacuum of space is predicted to become birefringent, meaning it would actually split light into two beams with different polarization states. This quantum effect would subtly alter the polarization signature of the light traveling through it, creating anomalies that cannot be explained by classical magnetic field structures alone. If this is the case, then these strange twists of polarized light are not just a sign of tangled fields. They are a direct glimpse into quantum effects playing out on a cosmic scale, a potential window into physics that we can never hope to recreate in any laboratory on Earth. Moving from the enigmatic twists of polarized light, we encounter a phenomenon that adds a splash of mysterious color to the nebula's palette, a subtle, ethereal blue haze that lingers in specific regions. This isn't the brilliant blue of synchrotron radiation we expect from high-energy electrons. It's a softer, more diffuse glow that seems to emanate from nowhere in particular. When astronomers analyze its spectrum, they find it doesn't match the signature of any known atomic transition or molecular emission. It's a ghostly light without a source, a color without a cause, and its presence points to physical processes so extreme they border on the theoretical. The challenge this blue haze presence is fundamental. In astronomy, light is a message, and every color tells a story about the element that created it or the mechanism that energized it. We have a well-stocked toolbox of explanations. Hydrogen gas glows red, oxygen glows green, and synchrotron radiation from electrons gives us a broad spectrum of light. But this particular shade of blue fits none of these categories. It's an orphaned wavelength, and its very existence forces us to consider that the nebula might be generating light through a process we've never directly observed in a cosmic setting before. One of the most thrilling theories proposed to explain this haze involves a phenomenon usually reserved for nuclear reactors and particle accelerators here on Earth: Cherenkov radiation. This beautiful, eerie blue glow is produced when a charged particle, like an electron, travels through a medium faster than light can travel through that same medium. It's a luminous sonic boom, an optical shockwave. In water, for instance, light slows down, allowing particles to outpace it and create that characteristic blue light. But space is mostly a vacuum where light travels at its maximum speed. Nothing should be able to outrun it, making true Cherenkov radiation impossible. So how could it appear in the Crab Nebula? The answer might lie not in the emptiness of space, but in the nebula's own dense, complex structure. While the space between stars is a near-perfect vacuum, the interior of a supernova remnant is not. It is filled with a tenuous but widespread plasma, a soup of ionized gas. The index of refraction for light passing through a plasma is not exactly 1. It's ever so slightly greater than 1, meaning light travels through it just a tiny fraction slower than it does through a perfect vacuum. Now consider the particles accelerated by the Crab Pulsar. We already know they reach energies that are almost incomprehensible, very likely hitting 99.99% of the speed of light. It is theoretically possible that these ultra-relativistic particles could, for a brief moment, be moving faster than light can travel through the local plasma medium. If even a fraction of these particles are doing this, they would generate a faint, diffuse Cherenkov glow, a blue haze that would be incredibly difficult to detect but would perfectly match the mysterious observation. An alternative, and perhaps even more exotic, explanation draws from the bizarre world of quantum electrodynamics. The magnetic fields around the pulsar are among the strongest known in the universe. In such an intense field, the quantum vacuum itself is predicted to behave like a strange crystal. One of the most peculiar effects is called vacuum birefringence. This means that the vacuum can actually split a beam of light into two rays, just as a calcite crystal does, and it can also affect how light is emitted in the first place. It's possible that the process of synchrotron radiation itself is being subtly altered by the quantum properties of the vacuum in these ultra-strong magnetic fields. The normal, predictable emission of light could be shifted, creating a modified spectrum that includes this unusual blue component. We would be seeing, for the first time, the light of a universe where empty space is not truly empty, but an active medium that can shape and color the light passing through it. Whether it's particles punching through a plasma faster than light can travel, or the quantum vacuum itself twisting the laws of emission, the blue haze is more than just a curious color. It is a direct probe into the most extreme conditions physics can produce. Its faint glow is a beacon, pointing toward processes that we can only theorize about and offering a rare chance to test our most advanced ideas about how matter and energy behave at their absolute limits. While the Crab Nebula puts on a dazzling show in visible light and X-rays, some of its most bizarre behavior is revealed in the warmth of infrared light, a glow we feel as heat rather than see with our eyes. Powerful space telescopes like Spitzer and Herschel have trained their infrared eyes on the nebula, expecting to see the steady, warm glow of cosmic dust, the microscopic silicate and carbon grains that should be evenly heated by the pulsar's intense radiation. Instead, they've recorded a light show with a mind of its own. Specific regions of the nebula flicker and change in infrared brightness over months and years, flaring up and fading in a rhythm that is completely out of sync with the pulsar's steady beat or the behavior seen in any other part of the spectrum. It's as if the nebula's heating system has a faulty, unpredictable thermostat, and this disconnect points to processes of dust creation and destruction that are far more dynamic and mysterious than we ever anticipated. The heart of the mystery lies in this complete lack of correlation. The pulsar is the nebula's central engine, pumping out energy with metronomic regularity. The X-ray and optical light generated by its wind and shock waves, while variable in their fine details, generally follow patterns we can link back to this powerful source. But the infrared variations operate on their own schedule. A dusty knot might suddenly grow brighter in infrared for a year, while the visible light from that exact same region remains completely unchanged, and the pulsar's spin continues its steady, slow decline. This tells us that the mechanism governing the infrared light is not directly tied to the main power supply. It's a secondary process, a hidden interaction happening within the dusty fabric of the nebula itself that we are only just beginning to detect. One compelling explanation for this strange behavior is a violent cycle of dust formation and destruction. The environment within the crab is incredibly harsh. It's flooded with high-energy radiation that can blast apart delicate dust grains in a process called sputtering. But it's also rich with the raw materials for making new dust, atoms like carbon, silicon, and oxygen that were forged in the progenitor star and blasted outward in the supernova. Astronomers theorize that this could create a chaotic, ongoing battle. In localized regions, conditions might briefly become just right for these atoms to clump together and form new microscopic dust grains. As this fresh dust condenses, it would rapidly absorb the pulsar's radiation and heat up, causing a sudden spike in infrared brightness. Shortly after, a wave of destructive radiation or a shock wave from the pulsar wind could rip through that same region, vaporizing the newly formed grains and causing the infrared glow to vanish as quickly as it appeared. An alternative, and perhaps even more fascinating, idea involves the dust grains themselves acting not as passive passengers but as dynamic participants. These aren't simple specks of dirt, they are likely complex, fluffy structures more like cosmic snowflakes. If a region of the nebula experiences a sudden change in density or a shift in the local magnetic field, it could cause these fragile grains to collide and stick together, forming larger aggregates. A larger grain has a different surface area and efficiency for absorbing heat, which would change its infrared signature. Conversely, a powerful shock wave could shatter these larger aggregates back into tiny fragments. This continuous process of construction and demolition would make the infrared output of any given region incredibly volatile, flickering as the population of dust grains constantly shifts in size and structure. The most profound possibility, however, is that we are witnessing a completely unknown heating mechanism. Our standard model assumes the dust is heated uniformly by the general radiation field from the pulsar. But what if the energy isn't delivered gently and evenly? The pulsar wind is likely filled with microscopic knots of intense energy, perhaps tiny magnetic shocks or concentrated packets of particles. If one of these microscopic energy bullets were to slam into a cloud of dust, it would deposit a huge amount of heat in a very localized area, causing a temporary, brilliant infrared flare. The rest of the dust not hit by this bullet would remain cool. This would explain the strange, isolated nature of the flares and their lack of connection to the pulsar's overall activity. The time variations in infrared are more than a minor curiosity. They are a signpost pointing to a hidden, turbulent world of creation and violence happening within the seemingly tranquil dust clouds. A world where the very building blocks of planets are constantly being forged and annihilated in a cycle we are only beginning to perceive. Surrounding the pulsar, extending light years into space, is its magnificent and utterly confounding legacy, a vast bubble of energized particles known as the Pulsar Wind Nebula. This is the engine room of the Crab, the visible manifestation of the pulsar's incredible power. For decades, astronomers have used sophisticated computer simulations to model how this structure should form, based on our understanding of fluid dynamics and magnetism. The basic idea is elegant. The pulsar's relativistic wind, a hurricane of electrons and positrons, expands outward until it smashes into the slower-moving shell of gas from the ancient supernova. This collision should create a roughly spherical shock wave that lights up the entire interior. But when we compare these neat, symmetrical models to the actual, intricate tapestry revealed by our most powerful telescopes, the two images could not be more different. The real wind nebula is a tangled, asymmetrical, and dynamically complex beast that refuses to conform to any simple explanation. The most striking features that defy our models are the bizarre, highly structured toroidal and jet-like formations embedded within the chaos. The term toroidal simply means donut-shaped, and that's exactly what we see. A vast, luminous ring encircling the pulsar's equator, perpendicular to its spin axis. Meanwhile, shooting out from the pulsar's poles are two powerful, narrow columns of energy, the jets that stab outward like searchlights into the depths of the nebula. This entire structure, this intricate machine of rings and jets, is sculpted by the pulsar's incredibly powerful magnetic field, which acts like a cosmic funnel, ruthlessly collimating the chaotic wind into these ordered outflows. The mystery isn't that these features exist, but that they persist over such vast distances without disintegrating into the surrounding turbulence. The conundrum lies in their stunning stability. These are not solid structures, they are patterns of energy flowing through a maelstrom at nearly the speed of light. The jet, in particular, should be highly unstable. According to hydrodynamics, such a narrow, fast-moving stream should be vulnerable to a host of instabilities like the Kelvin-Helmholtz instability, which causes wind to ripple over water. That would cause it to break apart, wobble, or dissipate within a very short distance. Yet the Crab's jets remain remarkably straight and coherent, punching through the nebula for light years without faltering. It's as if an invisible scaffold is holding them together, a force we cannot see that maintains their perfect form against all the forces trying to destroy them. This suggests that our models are missing a crucial ingredient, perhaps related to the magnetic field's strength and structure at these scales, which provides a form of rigidity to the flow that we don't yet fully understand. Furthermore, the entire system is tilted. The donut-shaped torus is not perfectly aligned with the jets, and neither are aligned with the overall oval shape of the outer nebula. This misalignment creates a bizarre, warped geometry that is incredibly difficult for simulations to reproduce. It suggests that the birth of the pulsar during the supernova explosion was not a clean, symmetrical event. The collapsing star must have experienced a violent, off-kilter kick, imparting a spin axis and a magnetic field axis that were never properly aligned to begin with. The pulsar wind nebula we see today is therefore a fossil record of that violent birth, its twisted shape preserving the chaos of its first moments 1,000 years ago. Unraveling this mystery is key to understanding not just the Crab, but all pulsar wind nebulae throughout the universe. These objects are nature's most powerful particle accelerators, and their structure dictates how energy is distributed and particles are energized. The strange stability of the Crab's jets implies that these accelerators are far more efficient and focused than we thought, capable of channeling energy across vast distances of space. Each new observation of this complex wind pushes our simulations to become more sophisticated, forcing us to incorporate stronger magnetic fields, more complex plasma physics, and the messy reality of a supernova's aftermath. The Wind Nebula is a cosmic masterpiece of ordered chaos, a beautiful reminder that even our best models are just a simplified sketch of the universe's incredible complexity. Just when we think we have a handle on the Crab Pulsar's rhythm, it commits its most audacious act of defiance. It simply stops talking to us. For minutes or sometimes even hours, its reliable radio pulse, the very signal that defines it as a pulsar, vanishes completely from our telescopes. The celestial metronome doesn't just skip a beat, it falls utterly silent, as if someone flipped a switch deep within the star. Then, just as mysteriously and without any warning, the radio beacon flickers back to life, returning to its precise 30 Hz rhythm as if the entire blackout never happened. These radio silence periods are among the most perplexing behaviors observed in any pulsar, and they point to a fundamental instability in the very mechanism that generates its most famous signal. The challenge in understanding these silences lies in their apparent randomness and the complete absence of any other change. During these quiet periods, the pulsar doesn't slow down. Its incredible X-ray and gamma-ray emissions continue unabated, proving that the central engine, the spinning neutron star itself, is still running at full power. It's not that the star has died, it's that its radio voice has been suddenly muted. This tells us that the radio emission is not generated by the core spin itself, but by a separate, more delicate process happening in the star's magnetosphere, the vast region of space dominated by its magnetic field. Something in that complex environment is periodically breaking down, severing the connection between the powerhouse and its radio broadcast. One of the leading theories for this strange muting focuses on the peculiar state of matter within the magnetosphere. This region isn't empty, it's filled with a seething plasma of electrons and their antimatter counterparts, positrons, ripped from the star's surface and accelerated to near light speed. The creation of this plasma is absolutely essential for the radio emission process. Think of it like a complex electrical circuit. The plasma provides the conductive pathway that allows the energy from the pulsar's spinning magnetic field to be transformed into the coherent radio waves we detect. Scientists speculate that during a silence period, this plasma supply might be temporarily choked off. The conditions needed to pull particles from the star's surface or to produce them from gamma rays could briefly fail, leaving the magnetosphere devoid of the charged particles it needs to complete the circuit. Without this plasma, the radio beam simply cannot form, and the pulsar goes radio dark until the delicate conditions for plasma creation are somehow restored. An alternative and equally fascinating idea suggests the problem isn't a lack of plasma, but an overabundance of it. If the plasma density were to suddenly and dramatically increase beyond a critical threshold, it could actually become too effective a shield. This super-dense plasma could act like an impenetrable fog, absorbing the radio waves as they try to propagate outward or smothering the formation of the beam at its source. In this scenario, the pulsar's own brilliance becomes its enemy. A temporary surge in particle production could clog its emission mechanism, silencing its own voice until the excess plasma can somehow dissipate or be cleared out by the pulsar wind. Perhaps the most intriguing theory looks beyond the pulsar itself to its dynamic relationship with the nebula. The Crab Pulsar is not sitting in a quiet vacuum. It's embedded in the violent, swirling gases of its own making. It's possible that denser clumps or filaments of nebula material could occasionally drift across our line of sight to the pulsar. While this neutral gas wouldn't affect the higher energy X-rays or gamma rays, it could easily absorb or scatter the longer wavelength radio waves, effectively casting a temporary shadow that makes the pulsar appear to turn off from our earthly perspective. If this is the case, the silence isn't originating from the pulsar at all, but is instead a theatrical effect created by the ever-shifting scenery of the nebula it illuminates. Each of these theories presents a captivating glimpse into the fragile balance of forces at work, suggesting that the pulsar's steady voice is not a given, but is instead the product of a precarious and easily disrupted cosmic dance. Yet for all the intense energy being poured into the Crab Nebula, there are regions within its vast cloud that present a cooling conundrum of their own, a mystery known as the temperature paradox. In the bizarre physics of space, hot things don't cool down like they do on Earth. There's no air to conduct heat away. In the near-perfect vacuum of a nebula, hot gas can only cool by radiating away its energy as light, a process that follows very predictable rules based on its density and temperature. Astronomers can therefore calculate exactly how fast a given cloud of plasma should cool. But when they apply these calculations to certain pockets within the crab, the numbers simply don't add up. These regions remain stubbornly, unexpectedly hot, as if they are being gently warmed by some hidden heater we cannot see, a source of energy that operates completely outside our current understanding of interstellar thermodynamics. The heart of this paradox is a fundamental disagreement between prediction and observation. We can measure the density of these hot regions. We can measure their temperature. From that, we can calculate their rate of energy loss through radiation. We can also measure the energy input they receive from the pulsar wind and the general radiation field bathing the nebula. In a stable, well-behaved system, the energy going in should equal the energy radiating out. But in these enigmatic zones, the energy radiating out is far less than it should be for their measured temperature and density. It's as if the plasma has found a way to become incredibly thermally efficient, somehow retaining its heat against all odds and defying the universal tendency to radiate energy into the cold of space. This isn't just a minor discrepancy. It suggests our entire model for how energy is managed within a plasma cloud might be missing a crucial piece of physics. One compelling explanation points to a form of cosmic insulation, a magnetic bottle effect. The Crab Nebula is laced with immensely powerful and complex magnetic fields. It's possible that in these specific regions, the magnetic field lines have become tightly wound and organized into a closed, cage-like structure. This magnetic cage could act as a nearly perfect insulator, trapping the hot plasma inside and severely restricting its ability to expand and cool. Furthermore, this confinement would also inhibit the plasma's ability to radiate its energy away efficiently. The charged particles need to move freely to emit synchrotron radiation, and if they are trapped by the magnetic walls of this invisible bottle, their ability to shed energy could be dramatically reduced. The region would appear to us as a persistent hotspot, not because it's being actively heated, but because it is being brilliantly protected from cooling down. An alternative and more active theory suggests we are missing a subtle but pervasive heating mechanism. The entire nebula is vibrating with powerful waves, sound waves, shock waves, and magnetohydrodynamic waves, generated by the churning pulsar wind and its collision with the outer shell. While most of the nebula is too diffuse for these waves to transfer significant energy, It's possible that in these denser, specific regions, the waves are being focused and absorbed. As these waves travel through the plasma, they could gradually deposit their energy as heat, much like ocean waves eroding a shoreline. This would provide a continuous, low-level heat source that counteracts the radiative cooling, maintaining the plasma at a higher temperature than our models predict. This process would be incredibly difficult to detect directly, as it would involve tracking the faintest of energy transfers across a vast and turbulent volume of space. Perhaps the most exotic possibility involves the very nature of the plasma itself. Under extreme temperatures and densities, plasma can enter regimes where collective behaviors dominate and the standard rules of ideal plasmas break down. The particles may begin to interact in ways that are not captured by our standard equations. It's conceivable that in these conditions, the plasma develops a form of internal dynamo, where motions within the cloud itself generate localized electrical currents and magnetic fields that provide a trickle of internal heating. This would be a self-sustaining process where the thermal energy of the plasma is constantly being recycled and topped up from within, creating a pocket of unexpectedly high temperature that is effectively decoupled from the external energy input from the pulsar. This temperature paradox forces us to look beyond the large-scale mechanics of the nebula and consider the intricate and hidden microphysics that govern how energy is stored and preserved in the most extreme environments in the universe. But the enigmas of the Crab Nebula extend beyond its flickering lights and silent moments. Some of its most compelling mysteries are written in the very motion of its constituent parts. When astronomers meticulously track the movement of individual knots and filaments over years and decades, they witness a cosmic ballet that defies all expectations. While the nebula is undoubtedly expanding from that initial cataclysm in 1054, many of its features refuse to follow the script. Instead of moving in a clean, radial pattern straight out from the center, some structures drift in completely unexpected directions, while others surge forward or lag behind at speeds that simple expansion models cannot explain. These peculiar movements, known as anomalous proper motions, paint a picture of a far more complex and dynamic interior than we ever imagined, suggesting the ghostly hand of unseen forces is sculpting the nebula from within. The standard picture of a supernova remnant is that of a single, powerful explosion sending a spherical shockwave plowing into the surrounding space. The debris from the star should be carried outward by this wave, with everything moving in a generally uniform and predictable way. The Crab Nebula shatters this simplicity. High-resolution observations from telescopes like Hubble reveal a chaotic and intricate dance. Certain bright filaments near the outer edges might be moving sideways or even slightly backward relative to the overall expansion. Meanwhile, some inner structures are rocketing outward at different velocities, creating a map of motion that looks less like an orderly exodus and more like a frantic crowd navigating an invisible obstacle course. This isn't the behavior of a simple blast wave. It's the signature of a system still violently reorganizing itself a millennium after its birth. So what could be causing this tangled web of motion? One of the most compelling explanations points to the immense and complex pressure of the pulsar wind nebula at the heart of the system. The pulsar wind is not a gentle, steady breeze. It is a fierce, anisotropic gale that blows more powerfully along the pulsar's equatorial plane and its polar jets. This means the interior of the nebula is not a uniform bubble of pressure. Some regions are subjected to a much stronger push from this relativistic wind than others. A filament located near the path of a jet might be violently accelerated forward, while a structure tucked between these high-energy outflows might experience less force, causing it to lag behind or be pushed aside by its faster-moving neighbors. The entire expanding shell of debris is being reshaped from the inside out by this powerful, uneven engine, creating currents and eddies in the flow of gas that account for the strange and varied directions of motion. Another fascinating possibility involves the invisible skeleton of the progenitor star itself. The star that exploded was not a featureless ball of gas. It had a complex structure with layers of different density and composition. It also likely had a strong magnetic field and was possibly rotating. When it exploded, this pre-existing architecture did not simply vanish. Denser pockets of material from the star's interior would possess more inertia, resisting acceleration and moving more slowly than lighter, fluffier ejecta. Meanwhile, the blast wave itself would have propagated unevenly through this structured medium, potentially creating secondary shock waves that ricocheted off denser regions and accelerated others. We could be witnessing the final echoes of that stellar structure, with the former anatomy of the dead star still governing the motion of its remains 1,000 years later. Perhaps the most mind-bending theory suggests the motions are clues pointing to something we cannot see, the gravitational influence of invisible mass. The case of the missing mass takes on a new dimension here. If a significant amount of mass from the progenitor star was transformed into dark matter or otherwise rendered invisible, it could still be exerting a gravitational pull on the visible gas. Lumps of this unseen mass distributed throughout the nebula would subtly tug on the glowing filaments, altering their trajectories and speeds in ways that appear entirely anomalous from our perspective. The proper motions we struggle to explain would then be a cosmic map, charting the distribution of this hidden material through its gravitational effects on the light we can see. Each unexpected jerk or turn of a filament is not random noise. It is a potential clue, a hint that the true structure of the Crab Nebula is far more massive and complex than the beautiful gaseous veil alone would ever suggest. This invisible shroud of high-energy light forms our next great puzzle, a phenomenon known as the gamma-ray halo. When our most powerful gamma-ray telescopes like the Fermi Space Telescope map the sky around the Crab, they detect something extraordinary. The nebula's brilliant gamma-ray heart is surrounded by a vast, faint, and incredibly extensive glow of this same high-energy radiation. This halo stretches far beyond the visible boundaries of the nebula itself, forming a tenuous sphere of light that should not, according to our best models, exist. We understand how the central pulsar creates gamma rays, but this colossal outer aura defies every prediction of how those particles should behave and spread, suggesting our grasp of cosmic particle physics is missing a fundamental chapter. The core of the mystery lies in a process called diffusion. Imagine the pulsar as a powerful fire hose, spraying a jet of ultra-energetic particles, primarily electrons and positrons, out into the nebula. Once these particles are launched, they don't travel in straight lines. They bounce and zigzag their way outward, trapped and scattered by the tangled magnetic fields that fill the space between the stars. This random walk journey is diffusion, and physicists have very precise equations to predict how fast these particles should spread from their source based on the strength and complexity of the local magnetic environment. For the Crab Nebula, these models make a clear prediction. Over the 1,000 years since the supernova, the highest energy particles should have diffused outward and created a gamma-ray halo of a certain calculable size. The actual halo observed by our telescopes is dramatically larger. The particles have somehow traveled much farther, much faster than the laws of diffusion should allow. It's as if someone provided them with a hidden network of cosmic highways, enabling them to race into the depths of interstellar space at a pace that leaves our textbooks in the dust. This glaring discrepancy forces astronomers to consider explanations that venture far beyond standard physics. One compelling line of inquiry suggests the culprit might be the magnetic fields themselves. Our models assume the interstellar medium around the Crab has a certain level of magnetic turbulence, but what if that turbulence is far weaker than we think? If the magnetic fields in this region are smoother and more orderly, they would offer far less resistance to the traveling particles. With fewer magnetic obstacles to bounce off of, the particles could maintain more of their original velocity and direction, allowing them to stream outward much more efficiently and create a larger, more extended halo than anticipated. This would mean our entire understanding of the magnetic landscape of our galaxy, at least in this local region, is fundamentally flawed. Yet an even more thrilling possibility whispers of a far more exotic source for this extended glow: dark matter annihilation. We know the Crab Nebula sits within a vast halo of this mysterious, invisible substance that permeates our galaxy. Certain theoretical models of dark matter propose that it consists of weakly interacting massive particles, or WIMP. If these particles ever collide with one another, they could annihilate on contact, converting their mass directly into pure energy and producing a shower of gamma rays, electrons, and positrons. If the dense core of the nebula, or the dark matter halo surrounding it, acts as a natural trap where these collisions are more likely, this process could be injecting a fresh population of high-energy particles right into the outskirts of the system. These newly created particles would then create their own diffuse gamma-ray glow, superimposing an unexpected and extended halo over the one produced by the pulsar. While still speculative, the sheer size and energy of the observed halo make it a perfect testing ground for these wild ideas, a potential window into the nature of the universe's most elusive substance. A third, and perhaps most profound, explanation re-examines the very nature of the pulsar wind. We tend to think of the particle acceleration as happening only at the central shock front near the pulsar. But what if that's not the whole story? It's possible that the powerful shock waves from the original supernova explosion are still propagating outward through the interstellar medium, far beyond the visible nebula. These ancient waves could still be acting as secondary particle accelerators. Furthermore, the pulsar wind itself might be capable of generating turbulence and shocks in the outer regions, creating new acceleration sites vast distances from the central engine. This would mean the gamma-ray halo isn't just made of particles that originated at the pulsar and then diffused outward. It's also being illuminated by particles that are being born and energized right there in the distant outskirts, in processes we have not yet even begun to map. The gamma-ray halo is therefore more than a simple glowing cloud. It is a cosmic cartogram, charting the secret pathways of energy and potentially revealing entirely new mechanisms through which the universe empowers its inhabitants. Even as we chart the visible motions of gas and the invisible spread of gamma rays, some of the most elusive messengers from the Crab Nebula are those that interact with almost nothing at all: neutrinos. These ghostly particles, so tiny and indifferent to matter that trillions pass through your body every second without a trace, are the ultimate cosmic spies, capable of fleeing the most chaotic environments unscathed. On rare occasions, massive detectors buried deep in Antarctic ice or submerged in the Mediterranean Sea have recorded a neutrino, and by tracing its path back across the cosmos, found it seems to point directly toward the Crab Nebula. This in itself is a fascinating discovery, but the real mystery lies in the energy and timing of these detections. They don't align with our predictions for how a pulsar wind nebula should produce these particles, suggesting that the Crab is operating a clandestine neutrino factory using physics we have yet to comprehend. The standard model for neutrino production in an object like the Crab is relatively straightforward and hinges on proton collisions. The pulsar's fierce wind is known to accelerate electrons to incredible speeds, which creates the brilliant synchrotron radiation we see. But if it also accelerates protons, the nuclei of hydrogen atoms, to similar relativistic energies, those protons can then collide with other protons or photons within the nebula. These violent impacts would create a shower of secondary particles, including short-lived pions, which then decay into gamma rays and, crucially, neutrinos. This process would create a steady, faint trickle of neutrinos that should be directly proportional to the nebula's gamma-ray output. The strange signals we detect, however, tell a different story. They occasionally arrive in small clusters or as single, very high-energy events that don't neatly correlate with flares or other activity in gamma rays or other wavelengths. It's as if the neutrino source is turning on and off independently, operating on its own secret schedule. This disconnect points to a production mechanism that is either far more efficient or entirely different from the standard proton collision model. One thrilling possibility is that we are seeing neutrinos born from the decay of ultra-heavy, exotic particles that could only be created under the nebula's most extreme conditions. The magnetic fields near the pulsar are so powerful that they might be capable of catalyzing processes predicted by theories beyond the standard model of particle physics. For instance, certain grand unified theories predict the existence of supermassive particles known as magnetic monopoles. If these hypothetical entities are present, they could catalyze proton decay, a process that would release a tremendous amount of energy and produce a burst of neutrinos with a unique signature. While this remains highly speculative, the Crab's environment is one of the few places in the universe where such bizarre physics could potentially play out. A more grounded, yet still profound, explanation involves the structure of the pulsar wind itself. Our models often treat the wind as a relatively smooth flow, but it is almost certainly riddled with microscopic knots of unimaginable energy, localized regions where the magnetic field is temporarily tangled into a super-intense knot. Within these tiny, transient accelerators, the conditions for particle acceleration could become unbelievably efficient. A single one of these magnetic knots could, for a brief moment, accelerate protons to energies far beyond what the average wind can achieve, leading to a sudden, intense burst of particle collisions and a resulting flash of high-energy neutrinos. This would explain the occasional nature of the detections. We are only catching the neutrinos when our telescopes happen to be looking during one of these microscopic, ultra-violent events within the greater wind. The implications of solving this mystery are enormous. If the Crab Nebula is producing neutrinos through a novel mechanism, it would confirm that these environments are even more powerful particle accelerators than we thought, capable of reaching energy frontiers we can only dream of replicating in labs on Earth. Furthermore, each neutrino that arrives from its direction is a pristine packet of information, carrying details about the conditions inside the nebula that are completely unobscured by magnetic fields or intervening matter. By deciphering their energy and timing, we could have a direct line into the heart of the most extreme physics in our galaxy, potentially uncovering new laws that govern how matter and energy behave under forces we can scarcely imagine. Yet another layer of deception is woven into the very fabric of the Crab Nebula, one that plays tricks on our most fundamental astronomical measurements. This is the phenomenon of the changing size illusion, where the nebula appears to wear a different mask for every instrument we point at it. When we map its boundaries in radio waves, we get one diameter. Switch to visible light and the size shrinks. Look in X-rays and the nebula seems to contract even further into a tight, energetic ball around the pulsar. These aren't small discrepancies, they are significant contradictions that, if taken at face value, would force us to conclude that the nebula is either expanding at different rates or is located at wildly different distances from Earth. This multi-wavelength masquerade forces us to abandon any simple notion of what this object truly looks like in 3 dimensions. The root of this illusion lies in a simple but profound truth. We are seeing only a 2-dimensional projection of a deeply complex 3-dimensional object. The Crab Nebula is not a hollow, painted bubble. It is a massive, intricate structure with a dense, energetic heart and a fainter, more diffuse outer halo. Different wavelengths of light are emitted by different physical processes, and these processes are not happening uniformly throughout the entire volume. Radio waves, for instance, are exceptionally good at penetrating dust and gas. They are emitted by lower energy electrons that can travel far from the central engine, allowing our telescopes to detect the faint, outermost reaches of the nebula's expansion, tracing its full, true extent. This gives us the largest possible measurement of its size. Visible light, however, tells a different story. This glow comes from the actual gas filaments, the shredded remains of the progenitor star, which are heated and set aglow by the pulsar's radiation. These filaments are not evenly distributed to the very edge of the radio halo. They are concentrated in a denser, more turbulent shell closer to the center. Our eyes and our optical telescopes see this bright, sharp-edged shell and naturally assume that this is the boundary of the nebula, resulting in a smaller measured diameter. Then we come to X-rays, the most energetic light of all. This emission comes from the highest energy electrons, those that have just been freshly accelerated at the powerful shock fronts near the pulsar. These electrons radiate away their tremendous energy very quickly, burning out like shooting stars before they can travel very far. Consequently, the brilliant X-ray glow is confined to the very inner regions of the nebula, creating the smallest apparent size of all. We are not looking at one object with three different sizes, but at three different components of the same object, each revealed by a different kind of light. Compounding this dimensional trickery is a breathtaking effect known as a light echo. The supernova of 1054 was a singular, cataclysmic flash of light, but that light did not simply vanish after it reached Earth. It continues to propagate outward into the interstellar medium, illuminating any dust or gas in its path. We are observing the nebula from a single, fixed vantage point, but the expanding shell of light from the original explosion is still traveling through space. This means that light from the same event can take slightly different paths to reach us, bouncing off dust clouds that are located at various distances along our line of sight. When this happens, we see a faint, ghostly replica of the nebula's structure that appears to be expanding at a rate that doesn't match its true motion. This echo can subtly alter the perceived edges and brightness of the nebula in certain wavelengths, further confusing our attempts to pin down its exact dimensions and expansion history. The changing size is therefore the ultimate testament to the nebula's complexity, a reminder that in astronomy, what you see depends entirely on how you choose to look, and that simple measurements can often hide a universe of depth. Woven through every one of these mysteries, from the ghostly rings to the silent pulses, is an invisible force that guides it all, the magnetic field. We can't see it directly, but its influence is everywhere, sculpting the jets, focusing the wind, and whipping particles to light speed. For decades, astrophysicists have worked to map this hidden architecture, using the polarized light from synchrotron radiation as their guide. This has allowed them to create sophisticated models predicting how strong the field should be and how it should be oriented throughout the nebula. Yet, when actual measurements from our most powerful telescopes are compared to these theoretical blueprints, the two maps bear little resemblance. The magnetic field we observe is a chaotic, unpredictable tapestry of strength and direction that refuses to follow any prescribed rules, suggesting our fundamental understanding of how magnetic fields are generated and sustained in such environments is deeply flawed. The core of the mystery lies in the field's shocking strength and its bizarre structure. Our models predicted that the magnetic field, born from the collapsed core of the star, would be immensely powerful near the pulsar, but would decay rapidly in strength as you moved outward, fading into the general background of the interstellar medium. Instead, measurements reveal that the field remains stubbornly strong even in the nebula's farthest reaches, possessing an energy density that rivals the kinetic energy of the expanding gas itself. This is like discovering that the magnetic field of a simple refrigerator magnet has enough power to halt a rushing river. Furthermore, the field's geometry is nothing like the clean, orderly dipole, a simple north-south bar magnet shape that our models assumed would dominate. Instead of smooth, flowing lines, we see a turbulent mess of knots, loops, and sudden reversals. a magnetic frenzy that looks more like a ball of twisted spaghetti than a structured cosmic force. This glaring disconnect forces scientists to consider that the textbook model for a pulsar wind nebula's magnetic field is missing a crucial ingredient, an ongoing dynamo process. We typically think of the magnetic field as a fossil relic, frozen into the neutron star at its birth and then simply carried outward by the pulsar wind. But what if the field is not just being carried, but is being actively amplified and regenerated as it goes? The interior of the nebula is a maelstrom of turbulent plasma, with different layers and clumps of gas moving at different velocities. This shearing motion could be acting like a natural dynamo, constantly stretching, twisting, and folding the magnetic field lines. Much like a mechanical generator converts motion into electrical current, this turbulent dynamo could be converting the kinetic energy of the swirling plasma into magnetic energy, continuously recharging the field and preventing it from decaying. This would explain its sustained strength far from the central engine, a phenomenon our static models never accounted for. An even more radical possibility is that the nebula is not a closed system. Our models assume the magnetic field is generated entirely from within, by the pulsar and its wind. But what if the crab is interacting with magnetic fields from the outside? The supernova exploded into a region of space that was not a perfect void. It was likely already laced with its own, weaker interstellar magnetic field. As the nebula expands, it could be sweeping up this pre-existing field, compressing it, and weaving it into its own internal structure. This would inject a completely foreign magnetic architecture into the system, one with its own history and orientation that would completely disrupt the clean pattern we expected from the pulsar alone. The chaotic knots and unexpected strengths we measure could be the result of this violent cosmic collision, a merger between the innate magnetic field of the dead star and the ancient magnetic landscape of the galaxy it exploded into. The implications of solving this magnetic mystery are profound. Magnetic fields are not passive players, they are the cosmic conductors that orchestrate the flow of energy and the acceleration of particles. If we don't understand the field's true strength and structure, we can never truly understand how the nebula shines, how the gamma ray flares erupt, or how the highest energy particles are born. Each anomalous measurement is a clue, pointing toward a more dynamic and interconnected universe than we ever imagined, where invisible forces are constantly being born, twisted, and reinforced in the turbulent aftermath of stellar death. But perhaps the most captivating theory is that the companion did not escape, but was instead consumed in a final, cosmic embrace. The supernova explosion was not a spontaneous event. It was the final act in a long and complex stellar drama. In a close binary system, the transfer of mass from one star to its partner can dramatically alter their fates. It's possible that the progenitor star was actively stripping material from its companion in the millennia leading up to the explosion. This process could have spun up the progenitor, enriched its outer layers, and ultimately triggered a different kind of supernova mechanism. Then, in the final cataclysm, the companion star, having been drawn incredibly close, might have been utterly engulfed by the expanding blast wave or gravitationally captured by the newly formed neutron star. We could be looking at the aftermath of a stellar merger, a violent union that left behind a single, rapidly spinning pulsar as the only testament to the binary system that once was. This would explain the pulsar's incredible spin. The infalling material from the consumed companion would have transferred a massive amount of angular momentum, acting like a cosmic whip that sent it spinning at its dizzying 30 times per second. The missing companion isn't missing at all, it's part of the pulsar itself, its substance and energy forever woven into the fabric of the object that destroyed it. Yet for all the grand mysteries of motion and magnetism, some of the most telling clues about the Crab Nebula's violent past are written in the language of chemistry itself, locked within the very atoms that make up its glowing filaments. When astronomers use spectrographs to perform a cosmic chemical assay, breaking down the light from different regions into its constituent elements, they expect to find a predictable pattern. A star of a certain mass should, in its death throes, forge a specific cocktail of heavy elements through supernova nucleosynthesis, and that mixture should be fairly consistent throughout the expanding wreckage. The Crab Nebula, however, serves up a bafflingly inconsistent menu. The ratios of elements like helium, oxygen, argon, and sulfur vary wildly from one filament to the next, with some regions curiously rich in certain elements while surprisingly poor in others. This patchwork chemical quilt defies our models of explosive element creation, suggesting the explosion mechanism itself was far from standard or that bizarre chemical processes have been at work in the millennium since. This isn't a minor inconsistency, it's a direct challenge to our understanding of stellar alchemy. The immense pressure and heat of a supernova are supposed to create a relatively well-mixed blend of new elements, with the explosion's shock wave thoroughly churning and distributing them. Finding such stark chemical differences across relatively short distances implies that this mixing was either incomplete from the very beginning or was somehow disrupted afterward. It's as if a master chef perfectly prepared a complex recipe, but then served it in separate bowls where the ingredients had settled into distinct, unmixed layers. For the Crab, this means the supernova explosion might not have been a single, symmetrical blast, but a more asymmetric or even fragmented event, leaving pockets of unmaterial from different layers of the progenitor star isolated from one another. One compelling explanation for this strange segregation points to the progenitor star's own anatomy. Stars are not uniform balls of gas. They are layered like an onion, with different nuclear fusion processes occurring in each concentric shell. The inner core fuses silicon into iron, surrounded by a shell fusing oxygen into silicon, then another fusing carbon into oxygen, and so on, all the way out to the outer layers of hydrogen and helium. Our models of a standard supernova assume the explosion does a reasonably good job of scrambling these layers together. But what if the Crab's explosion was different? Perhaps the shock wave that ripped the star apart was weaker in some directions or encountered unusual resistance from the star's internal structure. This could have resulted in a failed mixing scenario where chunks of debris from different layers, a piece of the helium shell here, a fragment of the oxygen layer there, were blasted outward more or less intact, preserving their unique chemical identities and creating the patchy distribution we see today. An even more dynamic possibility is that we are witnessing the effects of the pulsar wind itself, acting as a cosmic chemist over the last 1,000 years. The nebula is not a static museum exhibit. It is being continuously irradiated and reshaped by the pulsar's fierce output of energy and particles. This relentless bombardment could be actively altering the chemistry of the gas. For instance, the pulsar's intense radiation field could be selectively destroying delicate dust grains in certain areas. These grains are known to lock up certain elements like carbon and silicon. Destroying them would release those atoms back into the gas phase, enriching specific regions and changing the observed elemental ratios. Alternatively, the mechanical force of the pulsar wind could be physically sweeping and sorting the debris, pushing lighter elements like helium ahead of it while allowing heavier elements to lag behind, effectively performing a large-scale chemical separation that would never occur in a simple expanding blast wave. The most profound implication of these chemical anomalies, however, touches on the very nature of the explosion. The peculiar abundances, particularly the high levels of helium and certain isotopes of argon and sulfur, have led some scientists to reconsider the supernova type. The prevailing theory is that the Crab was an electron capture supernova, a rare type arising from a star in a specific mass range. This model makes precise predictions about the elemental yield. The fact that the observed abundances don't perfectly match these predictions suggests that the explosion mechanism might have been even more exotic. perhaps involving a magnetic field so strong it dominated the collapse, or a rotation so rapid it shredded the star in an unusual way. The strange chemistry is therefore a frozen record of the explosion's first milliseconds, a message encoded in elemental ratios that we are still learning how to read, offering a glimpse into the chaotic and poorly understood engine that powers a star's death. Just when we think we've mapped the Crab Nebula's every flicker and flare, it reveals a talent for time travel, or at least a brilliant illusion of it. This next phenomenon unfolds not in real time, but on a delayed reel, a cosmic encore that plays out years after the main event. Astronomers call these infrared light echoes, and they present a puzzle that goes far beyond simple reflections. Imagine watching a firework explode in the night sky, seeing the brilliant burst fade, and then, minutes later, seeing an identical burst appear somewhere else entirely. That's the bizarre effect we see in the Crab, but on a scale of years and across light years of space. A brilliant X-ray flare or a surge in optical brightness will occur at the pulsar, and then, years later, a ghostly, cooling infrared glow will suddenly appear in a completely different part of the nebula, as if the news of the explosion has only just arrived. The simplest explanation would be a literal echo light from the initial flash travels outward, hits a distant cloud of dust, and is reflected back toward us. Because the reflected light takes a longer path to reach our telescopes, it arrives later, creating the echo. But the Crab's echoes refuse to play by these simple rules. The timing is off, the geometry is wrong. Most puzzling of all is the color. These echoes appear specifically in the infrared, a much redder, cooler light than the original high-energy event. If it were a simple mirror-like reflection, we would expect to see a delayed but otherwise identical flash in the same type of light, an X-ray echo for an X-ray flare, for instance. The fact that the echo is transformed into infrared warmth suggests something far more complex is happening than mere reflection. It implies the distant dust cloud is not a passive mirror, but an active participant, absorbing the high-energy news and then rebroadcasting it in its own thermal voice. This points toward a process known as thermal reprocessing. Here's how it might work. A powerful blast of X-rays or ultraviolet light from a pulsar flare races out into the nebula. After traveling for years, it finally slams into a cold, dense filament of gas and dust located light years away from the central engine. This cloud absorbs the energetic radiation, but it doesn't just bounce it back. The energy heats the microscopic dust grains within the cloud, causing them to vibrate intensely and re-radiate that energy as a strong, warm glow in the infrared part of the spectrum. We see this delayed infrared brightening and call it an echo, but it's really more like a cosmic translation, a conversion of one form of energy into another, happening on a monumental timescale. This process acts as a fascinating delay tactic, allowing us to study the pulsar's most violent historical outbursts years after they occur, by simply watching for the warm-up act in the nebula's distant outskirts. Yet even this sophisticated thermal model might not be the full story. The precise timing and intensity of some echoes suggest the energy might not be released immediately. Some theories propose these distant dust clouds could be acting as tiny energy capacitors. The dust grains might absorb the high-energy radiation, but then release it only slowly over time, perhaps as they undergo subtle changes in their crystalline structure or as the heat diffuses through a very thick, dense cloud. This would stretch a sharp, instantaneous flash into a longer, smoother infrared glow, further complicating the connection between the initial cause and the distant effect. These infrared echoes are therefore more than just pretty ghosts. They are forensic evidence. By studying their location, timing, and color, we can literally map the distribution of cold, dark material throughout the nebula that is otherwise invisible to our telescopes, and uncover a hidden history of the pulsar's past tantrums written in the warm glow of distant dust. Deep within the chaos of the Crab Nebula, the universe seems to be hurling its most energetic particles directly at us, and some of them carry an energy signature that simply shouldn't exist. Our most sensitive particle detectors on Earth and in space have picked up a handful of these cosmic bullets, ultra-high energy cosmic rays and neutrinos that appear to originate from the crab's direction. The puzzle isn't just their incredible power, which can be millions of times greater than what the most powerful human particle accelerator can produce. It's that their energy level blatantly exceeds the theoretical maximum for a pulsar like the one at the crab's heart. According to our best models, there's a fundamental ceiling, a speed limit imposed by physics, on how much energy a spinning neutron star's magnetic field can impart to a single particle. These detections aren't just nudging against that ceiling, they're shattering it, forcing us to question whether our understanding of acceleration is completely wrong or if we're seeing the signature of something entirely new. The standard model for particle acceleration in a pulsar wind nebula is known as Fermi acceleration, a process where particles gain energy by repeatedly bouncing across a magnetic shock front, like a tennis ball being volleyed faster and faster between two approaching rackets. The size and magnetic strength of the shock wave ultimately determine the maximum speed a particle can achieve. For the Crab Pulsar, this puts a hard cap on the energy of any individual proton or electron it can launch. The mysterious particles we've detected blow right past this calculated limit. It's the equivalent of a slingshot launching a projectile at the speed of a railgun. The mechanism we think is at work appears fundamentally incapable of the result we're observing. This leaves scientists with two equally thrilling possibilities. Either the Crab Nebula is employing an acceleration trick we've never conceived of, or these particles aren't coming from the pulsar at all, but from the annihilation of invisible dark matter. The first possibility takes us into the realm of exotic plasma physics. Perhaps the acceleration isn't happening gradually at the main shock front, but in incredibly localized and transient events within the turbulent pulsar wind itself. Imagine microscopic magnetic tornadoes, fleeting knots of energy where the magnetic field lines snap and reconnect with unimaginable violence. These magnetic reconnection events could act not like a steady slingshot, but like an infinitesimally small and precise particle cannon, capable of concentrating all of their ferocious energy into a single, lucky particle, granting it an impossible boost in a 1 in a billion encounter. Another theory suggests that multiple acceleration sites could be working in a chaotic Chinese letter relay race. A particle might get a first kick from a reconnection event near the pulsar, then travel across the nebula only to be caught by a second shock wave from the supernova remnant's outer shell, gaining a second compounding kick that pushes it far beyond what any single process could achieve. The second, and even more profound, possibility is that these ultra-high-energy particles are our first direct glimpse of dark matter. We know this mysterious substance outweighs normal matter in the universe by a factor of 5 to 1, but we have never directly detected what it's made of. A leading candidate is a hypothetical particle known as a WIMP, a weakly interacting massive particle. If two such particles were to collide, they would annihilate each other in a flash of pure energy, converting their mass into a shower of secondary particles, including high-energy protons, electrons, and neutrinos. The dense core of the Crab Nebula, with its immense gravitational field, could act as a natural trap, concentrating dark matter particles to a density where these annihilations become more likely. The energy released in such an event would be staggering, easily capable of producing the extreme particles that leave our detectors baffled. If this is true, then the Crab Nebula is not just a cosmic accelerator. It's a natural laboratory, and these rare Chinese letter particles are the heralds of a hidden sector of physics, offering us a fleeting chance to study the invisible 85% of the universe's matter. Each detection is a message in a bottle, and we are only just learning how to break the code. Of all the dynamic structures within the Crab Nebula, none is more mesmerizing and unpredictable than the relativistic jet screaming from the pulsar's pole. This isn't a static searchlight beam, it's a living, shape-shifting serpent of pure energy. Time-lapse observations from our most powerful telescopes reveal a jet that writhes, kinks, and changes its direction of travel over months and years, performing a slow, cosmic dance that no simple model of a spinning top can explain. This isn't the steady wobble of precession we might expect from a gyroscope. It's a far more complex and turbulent motion, suggesting the forces controlling it are not just mechanical, but born from a constant, violent struggle within the pulsar's own magnetosphere and its fight against the nebula's chaos. The standard precession model is elegant in its simplicity. If the pulsar's spin axis and its magnetic axis are misaligned, which they almost certainly are, the entire star should wobble as it rotates, much like a child's top slowing down. This graceful wobble would cause the jet to trace out a gentle cone in space over a regular period. While some long-term changes might fit this idea, the jet's actual behavior is far more erratic. It doesn't just sweep a clean circle, it exhibits sudden jumps, develops temporary knots of intense brightness, and even appears to change its angle of attack in a way that suggests it's being buffeted by invisible winds or pinched by invisible forces. It's as if the lighthouse keeper is not just gently turning the light, but is also constantly and randomly bumping into it. This bizarre motion points directly to the incredible complexity of the magnetosphere, the region of space completely dominated by the pulsar's magnetic field. We often picture this field as a simple, orderly set of lines emanating from the star, but the reality is likely a seething, turbulent plasma where magnetic field lines are constantly breaking and reconnecting in explosive events. These magnetic reconnections aren't just happening at the base of the jet, they could be occurring throughout its length. A major reconnection event could suddenly release a knot of energized plasma, which would then shoot down the jet like a bullet train, appearing as a bright, moving knot on our images. Furthermore, these events could instantly reconfigure the local magnetic geometry that's guiding the jet, giving it a sudden and sharp kink in a new direction. The jet isn't just a passive beam, it's a dynamic flow that is constantly being reshaped by the stormy magnetic weather at its source. But the magnetosphere isn't the only actor in this play. The jet must also plow through the incredibly dense and messy environment of the inner nebula. It's not moving through a perfect vacuum, it's fighting its way through a fog of its own making, a fog filled with the debris of the supernova and the backflow of particles from the pulsar wind itself. The pressure from this surrounding medium is not uniform. Denser clumps of gas or regions of higher magnetic pressure outside the jet can act like celestial sandbars, deflecting its path and causing it to bend and sway. Imagine trying to hold a high-pressure fire hose steady in a hurricane. The jet is doing all it can to maintain its integrity against the chaotic, pushing forces of the nebula it's trying to escape. This interaction could be responsible for the larger-scale, slower wobbles we observe as the jet navigates an ever-shifting landscape of interstellar resistance. Perhaps the most profound possibility is that we are witnessing a feedback loop of incredible power. The jet itself, as it rams into the nebula, is actively changing the environment it's moving through. By depositing energy and momentum into the surrounding gas, it heats it and pushes it aside, effectively clearing its own path. But this altered environment then changes the conditions the jet encounters a moment later. This constant self-modification creates a highly dynamic and unpredictable system, where the jet's past actions directly influence its future shape and direction. Its movement isn't just a product of its birth, it's a real-time negotiation with its surroundings, a testament to the fact that in the heart of the Crab Nebula, nothing is ever truly stable or isolated. Every twist and turn of the jet is a coded message, detailing the intense and ongoing battle between structure and chaos, between the focused power of the pulsar and the tangled reality of the cosmos it inhabits. Now we come to a mystery that plays out not in a single moment, but across time itself, a phenomenon that forces us to question the very sequence of cause and effect within the nebula. These are the mysterious time lags, the strange and unpredictable delays between an event observed in one wavelength of light and that same event appearing in another. Imagine watching a lightning strike and hearing the thunderclap moments later. The delay tells you how far away the storm is, but in the Crab Nebula, the rules are different. Here, a brilliant X-ray flare might erupt from the pulsar, and the corresponding flash in visible light might not follow for hours, days, or even weeks. This isn't a simple delay due to distance. It's a fundamental disconnect that suggests the particles responsible for these different types of light are being produced, accelerated, and managed by completely separate processes, operating on their own secret timetables deep within the nebula's chaotic heart. This temporal mismatch is one of the most baffling observational quirks because it strikes directly at our standard model of how a pulsar wind nebula works. In the clean, textbook version, the pulsar's spinning magnetic field acts like a unified engine. It accelerates a population of electrons to near light speed all at once. These energized electrons then spiral around the magnetic field lines, and as they do, they simultaneously emit radiation across the entire electromagnetic spectrum, from radio waves all the way up to gamma rays. According to this simple picture, a surge of energy from the pulsar should cause an instantaneous, coordinated brightening at all wavelengths. The fact that we see a bright X-ray flare without an immediate optical counterpart, or vice versa, is like pressing the gas pedal in a car and watching the speedometer jump only after the engine has already been racing for a mile. It tells us the machinery is far more complex than we thought. So what could possibly be causing this bizarre desynchronization? One of the most compelling theories involves a cosmic sorting mechanism based on energy. The electrons being accelerated aren't all identical. They exist across a vast spectrum of energies. The highest energy electrons, which emit X-rays and gamma rays, radiate away their incredible power extremely quickly, burning out in a matter of days or even hours. Lower energy electrons, which produce visible light, can last for years before dissipating their energy. Now, imagine a sudden, violent event, like a magnetic reconnection near the pulsar, that gives a massive, one-time boost to a whole swarm of electrons. The highest energy electrons in that swarm would light up immediately in X-rays, blaze brilliantly for a short time, and then vanish. Meanwhile, the lower energy electrons from that same initial boost would take much longer to travel to the parts of the nebula where they emit visible light, and they would radiate their energy away over a much longer period. The initial cause is the same, but the different particle lifetimes create a dramatic time lag between the high energy and low energy light shows. Another fascinating possibility points to the complex geography of the magnetic field itself. The nebula is not a blank void, it's a labyrinth of magnetic structures. It's possible that the accelerated particles responsible for different wavelengths are actually produced in entirely different locations. The X-rays might be generated in a violent event very close to the pulsar, deep within the inner magnetosphere. The visible light, however, might be produced much farther out, where the particles finally slam into a dense wall of gas and cause it to fluoresce like a neon sign. If a disturbance originates at the pulsar, the news of that event carried by the particles themselves would take a significant amount of time to travel the light years to the visible light-emitting region. The particles creating the X-rays, being right at the source, would respond instantly. This would create a predictable delay, a literal travel time for the news of the explosion to reach the outskirts of the nebula and trigger a visible response. Perhaps the most mind-bending explanation is that we are not looking at one single event but a chain reaction. The initial flare in X-rays might not be the cause of the later optical event at all. Instead, that X-ray blast could be the trigger for a secondary process. For example, a powerful wave of X-ray radiation could blast outward from the pulsar and days later slam into a distant cold cloud of gas and dust within the nebula. The impact of this radiation would violently heat the dust, causing it to glow brightly in the infrared and optical spectrum. In this scenario, the time lag isn't a delay within a single process. It's the interval between the initial cause and its first effect on a completely separate part of the nebula. The mysterious time lags are therefore a powerful diagnostic tool. By carefully measuring these delays, astronomers can literally map the structure of the nebula and the travel times for energy within it, turning a puzzle of timing into a blueprint for the invisible cosmic machine. Moving outward from the pulsar through the swirling clouds of the Crab Nebula, we expect the furious energy to gradually fade, the way a campfire's warmth diminishes the farther you step away from the flames. This expectation is rooted in one of the most reliable principles of physics, the inverse square law. It's a simple but powerful rule stating that the intensity of radiation weakens with the square of the distance from its source. A light bulb looks blinding up close but appears as a faint speck from a mile away. For the Crab Nebula, this means its radio brightness, generated by synchrotron radiation from electrons spiraling around magnetic fields, should drop off dramatically as we look farther from the central pulsar. Yet when radio astronomers map the nebula, they are met with a stunning contradiction. The radio glow remains stubbornly, inexplicably strong even in the nebula's outermost, most remote regions. This is the radio brightness paradox, a quiet but profound rebellion against a fundamental law that suggests the nebula's heart is not its only engine. This isn't a minor deviation or a measurement error. It's a glaring anomaly that forces us to reconsider how energy is distributed within this cosmic cloud. The pulsar is undeniably the primary powerhouse, but its influence should wane with distance. The fact that the radio emission holds its strength across light years implies that the electrons responsible for this radiation are not simply coasting away from their source, slowly losing energy as they travel. Instead, they must be receiving a continuous boost, a steady supply of energy that replenishes them throughout their journey, allowing them to shine as brightly in the distant outskirts as they do near the furious core. It's as if someone has secretly installed a series of booster stations along a highway, ensuring a car maintains its top speed for the entire length of its trip rather than gradually slowing down. So where is this hidden energy coming from? The most compelling explanation points to a vast network of secondary accelerators scattered throughout the nebula. The Standard Model places the main particle acceleration site at the termination shock, the region where the pulsar's fierce wind slams into the slower-moving nebula material. But the radio paradox suggests this single, central event isn't the whole story. The interior of the Crab is a turbulent sea of moving gas, tangled magnetic fields, and powerful shock waves. It's likely that this chaotic environment is riddled with smaller, yet still immensely powerful shock fronts. These could be generated as the pulsar wind interacts with denser clumps of gas or as large-scale bubbles of plasma collapse and rebound. Each of these smaller shocks could act as its own miniature particle accelerator, giving local electrons a fresh kick of energy and ensuring the radio glow remains strong far from the central engine. Another fascinating possibility involves the magnetic field itself acting as a continuous energy source. The magnetic fields within the nebula are not static, they are dynamic, moving structures. As these field lines stretch, twist, and reconnect, they can release enormous amounts of stored energy directly into the particles trapped within them. This process, known as magnetic reconnection, is like stretching a rubber band to its limit and then snapping it, converting the stored tension into a sudden, violent motion. If reconnection events are happening continuously throughout the volume of the nebula, they could provide the steady trickle of energy needed to keep the electrons energized, effectively making the entire nebula itself one giant diffuse accelerator. The radio brightness would then be a map not of a fading central source, but of this ongoing, distributed magnetic activity. This paradox does more than just present a puzzle. It fundamentally changes how we view the Crab Nebula's role in the galaxy. It suggests that these spectacular remnants are not merely passive clouds illuminated by a central star, but are active and efficient engines in their own right. They seem capable of taking the raw power from a pulsar and amplifying it, spreading it out, and sustaining it across a vast volume of space. This process of continuous acceleration could be crucial for seeding the galaxy with high-energy particles, contributing to the cosmic ray background that permeates the interstellar medium. The unwavering radio glow from its farthest edges is a silent testament to this hidden vitality, proving that even in its apparent stillness, the Crab Nebula is teeming with unseen power. At the very poles of this cosmic powerhouse, where its magnetic field should be most focused and intense, we find features that refuse to conform to our expectations. Deep within the swirling chaos of the Crab Nebula, the pulsar's polar caps are not the smooth, predictable emission zones our models predicted. Instead, high-resolution observations, particularly in X-rays, reveal a bizarre and mottled landscape. Rather than symmetrical, well-defined hotspots, we see emission that is patchy, uneven, and often strangely offset from the magnetic axis. It's as if the lighthouse's lamp isn't a single, perfect bulb, but a cluster of flickering, misaligned lights, some of which seem to wander around the pole. This isn't just a minor imperfection. It's a fundamental challenge to our understanding of how a pulsar's most fundamental feature actually works. The standard model for polar cap emission is a study in elegant simplicity. We picture the pulsar's immense magnetic field ripping electrons and their antimatter counterparts, positrons, from the star's solid crust at the magnetic poles. These particles are then accelerated to nearly the speed of light along the curving magnetic field lines, and as they are flung out into space, they radiate a focused beam of energy. This process should create a pair of bright, relatively uniform hotspots directly over the magnetic poles. But the reality we observe in the Crab is a messy, asymmetric glow that shifts and changes. This forces us to consider that the surface of this neutron star is anything but a smooth, featureless sphere. One of the most captivating explanations for this strange topography involves the concept of starquakes on an almost unimaginable scale. The pulsar's crust is not a passive shell. It's under incomprehensible strain, stretched and compressed by the star's insane rotation and its own titanic magnetic forces. This strain could cause the crust to crack, creating vast mountain ranges that are mere centimeters high but stretch for kilometers across the surface. While these mountains are tiny in relative height, their mass is enormous due to the neutron star's incredible density. A mere teaspoon of this material would weigh billions of tons. The gravitational pull of such a feature could locally distort the magnetic field lines, bending them away from a perfect geometry. This distortion would change the path of accelerated particles, focusing the emission into an irregular, off-center hotspot, or even creating multiple, smaller hotspots around the true magnetic pole. We wouldn't be seeing the pole itself, but its brilliant reflection in a twisted magnetic mirror. Another possibility delves into the bizarre physics of the star's interior. The crust is believed to float atop a superfluid core of neutrons, a quantum realm where friction ceases to exist. The interaction between this swirling superfluid and the solid crust above it is poorly understood and could be highly unstable. Vortices of superfluid energy might periodically punch through the crust like geysers, creating temporary, intensely hot spots that erupt with particle emission before fading away. These thermonuclear geysers would appear as transient bright patches near the pole, flickering on and off in a rhythm that has nothing to do with the star's rotation, adding a layer of unpredictable volatility to the polar landscape. The uneven emission wouldn't be a structural feature, but a sign of the violent turmoil seething just beneath the surface. perhaps the most profound explanation re-examines the magnetic field itself. Our models often assume a relatively pure dipole field, a simple, giant bar magnet shape. But what if the field in the immediate vicinity of the star's surface is far more complex? It could be a tangled web of higher-order magnetic components, quadrupole and octupole fields, that create a multitude of smaller secondary poles very close to the main ones. In this scenario, the pulsar wouldn't have two clean poles, but a cluster of mini-poles all vying for dominance. Particle acceleration and emission would then happen from several of these smaller sites simultaneously, creating the patchy, complicated pattern of hotspots we observe. The polar cap isn't a single feature, it's a fractured magnetic archipelago, and we are seeing the combined light of its many islands. This would mean the magnetic field at the neutron star's birth was imprinted with a complexity we are only now beginning to detect, a fossil record of the chaos that accompanied its formation 1,000 years ago. Yet for all the intricate puzzles of timing and structure, the most profound challenge to our understanding of the Crab Nebula may come from a single, comprehensive measurement, its total energy spectrum. This is not about a single wavelength or a fleeting event, but the entire grand summary of its light output, from the lowest energy radio waves to the most penetrating gamma rays. For decades, astrophysicists have possessed the master equation to explain this spectrum. It's a two-part model built on two brilliant pillars of physics: synchrotron radiation and inverse Compton scattering. According to this elegant theory, the story should be complete, but the Crab Nebula's actual energy signature tells a far more complicated and mysterious tale, with glaring features that this standard model cannot account for, forcing us to consider that entirely new chapters of physics remain to be written. Let's break down this established model, this beautiful theory that now appears to be cracking under the weight of new data. The first pillar is synchrotron radiation. We know the pulsar's fierce wind accelerates electrons to nearly the speed of light. As these ultra-relativistic electrons are forced to spiral along the nebula's powerful magnetic field lines, they emit energy across a vast spectrum, from radio waves up through infrared, visible light, and into X-rays. This process creates a smooth, continuous curve of emission that dominates the lower energy part of the spectrum. The second pillar is inverse Compton scattering. Those same high-energy electrons don't just radiate their own energy, they also play a game of cosmic pool with existing lower-energy photons. The photons of the cosmic microwave background, the faint afterglow of the Big Bang, or even the synchrotron photons themselves collide with the ultra-fast electrons. In these collisions, the electrons transfer a massive amount of energy to the photons, boosting them from their humble origins way up into the highest energy regime of gamma rays. Together, these two mechanisms should paint a perfect, self-consistent picture of the nebula's energy output from one end of the spectrum to the other. But when we overlay this theoretical curve onto the actual data collected by our most advanced telescopes, the match is far from perfect. There are noticeable bumps, wiggles, and excesses of light at specific energies, particularly in the high-energy gamma-ray regime, that the model simply cannot reproduce. It's as if an artist painted a beautiful, smooth gradient, only for another hand to dash across it with a brush of a completely different color. These spectral anomalies are the ghostly fingerprints of processes we have not yet identified, suggesting that our two-pillar model, while brilliant, is tragically incomplete. The nebula is not just doing what we expect, it's performing extra, hidden work that we are only now beginning to detect. One of the most thrilling possibilities is that we are seeing the signature of an entirely different population of particles. Our standard model focuses almost exclusively on electrons and their antimatter twins, positrons. But what if the pulsar's accelerator is also slinging protons into the mix? Protons are over 1,000 times heavier than electrons, and when accelerated to similar relativistic speeds, they carry vastly more energy. While they don't produce synchrotron radiation efficiently, they do create gamma rays through a different, more violent process, hadronic collisions. A relativistic proton slamming into a slower moving proton from the background gas can create a shower of secondary particles, including neutral pions that immediately decay into very specific high-energy gamma rays. This would create a distinct bump or excess in the spectrum at those energies, a feature that the purely electron-based model cannot explain. If confirmed, this would be a monumental discovery, proving that the Crab Nebula is not just an electron accelerator, but a cosmic hadron collider capable of energizing the building blocks of matter itself. An even more exotic explanation ventures beyond known particles altogether. The persistent anomalies in the spectrum, particularly at the very highest energies, could be the long-sought signature of dark matter annihilation. If the dense core of the nebula has accumulated a sufficient density of these hypothetical particles, their mutual annihilation would produce a spray of standard model particles, including electrons, positrons, and gamma rays with a very specific energy signature. This would inject an entirely new source of particles and energy into the system, superimposing its own unique spectral features on top of the familiar synchrotron and inverse Compton glow. While still a speculative idea, the Crab's stubborn refusal to conform to standard models makes it one of the most promising places in the sky to hunt for these ghostly signals from the dark sector. Perhaps the most profound possibility is that we are witnessing the limitations of our own physical theories. The conditions within the Crab Nebula are so extreme, with magnetic fields trillions of times stronger than Earth's and particles moving within a fraction of a percent of light speed, that our standard equations for radiation mechanisms might simply break down. Quantum electrodynamic effects that are negligible in every other astrophysical context could become dominant here, subtly altering how light is emitted. The vacuum itself, under such incredible magnetic stress, might become a birefringent medium that polarizes and shifts light in ways we can't yet calculate. The energy spectrum mystery is therefore more than just an accounting error. It is a direct challenge, a complex code written in the language of light that, if we can decipher it, could reveal entirely new laws governing how energy, matter, and radiation interact under the most extreme conditions the universe can muster. And now we arrive at our final and perhaps most humbling mystery, one that forces us to question the very constancy of the heavens. For centuries, astronomers have meticulously recorded the Crab Nebula's brilliance, creating a historical light curve that stretches back to its dramatic birth. When we compare those ancient observations with the nebula's measured brightness today, we are confronted with a startling and inescapable conclusion. According to multiple, independent records, the Crab Nebula was significantly brighter in the past, not by a small margin, but by a factor that our current physical models of its emission simply cannot account for. This isn't a case of fuzzy historical data. It's a glaring discrepancy that suggests either our measurements are fundamentally flawed, or the nebula itself has undergone a profound physical transformation that we have failed to anticipate. The evidence for this historical brightening comes from a diverse array of sources, each adding a layer of credibility to the claim. Early 20th century photographic plates, taken by astronomers using the most advanced technology of their day, consistently show a nebula that appears more luminous than it does in modern digital images. Even more compelling are visual estimates made by highly skilled observers throughout the 18th and 19th centuries, who often describe the crab with a brilliance that seems almost exaggerated by today's standards. The most straightforward interpretation of this data is that the nebula has genuinely faded over the last century or more, but this is where we hit a monumental wall. Our detailed understanding of how a pulsar wind nebula evolves and how synchrotron radiation fades over time predicts a very specific and very gradual rate of dimming. The historical records suggest a decline in brightness that is far too rapid, creating a paradox that leaves modern astrophysicists scratching their heads. This forces us to confront two radically different possibilities, each with profound implications. The first and more conservative explanation is that we are dealing with a pervasive and subtle calibration error spanning generations of astronomy. The tools and techniques for measuring the brightness of faint, extended objects like the Crab Nebula have changed dramatically over the decades. Photographic emulsions on glass plates have vastly different sensitivities to light compared to modern charge-coupled devices, or CCDs. The filters used to isolate specific wavelengths of light were not standardized, and the very definition of the magnitude system used to quantify brightness has been refined over time. It is entirely possible that when we carefully correct for all these known instrumental effects, the historical brightness anomaly will simply vanish, revealing a nebula that has faded at exactly the rate our physics predicts. This would be a triumph of meticulous data archaeology, but it would also mean that a fascinating mystery was merely a mirage created by our own evolving technology. The second possibility, however, is far more thrilling. What if the records are correct? What if the Crab Nebula was genuinely brighter a century ago? This would mean that our models of its physics are incomplete in a fundamental way. We assume the nebula's glow is powered by a central engine, the pulsar that is slowing down at a steady and predictable rate. But what if that engine itself has changed? A sudden and major glitch or spin-down event in the pulsar's past, far larger than any we've observed in the modern era, could have injected a massive, one-time burst of energy into the nebula. This energy would have taken time to dissipate, causing a sustained period of elevated brightness that has only now faded to the level we consider normal. We would have missed this ancient cataclysm, only seeing its long-term aftereffects in the historical light curve. An even more exotic idea involves the nebula's environment. Perhaps the interstellar medium through which the crab is expanding is not uniform. If the nebula plowed into a slightly denser cloud of gas in the recent past, the increased resistance would have caused the forward shock to compress and temporarily heat up. This would have made the entire structure shine more brightly for a period of decades or even centuries, before it eventually broke through into less dense space and returned to its expected luminosity. We would be seeing the echo of a cosmic traffic jam recorded in its historical light. The implications of this historical anomaly are therefore immense. If it's real, it means the Crab Nebula is not a static laboratory but a dynamically aging creature whose past behavior holds clues to events we never directly witnessed. It serves as the ultimate reminder that our snapshot view of the cosmos is just that, a single frame in a billion-year movie, and we are only just beginning to learn how to read the plot. So as we've journeyed through these 30 strange phenomena, from the pulsar's immortal spin to the ghostly infrared echoes and the paradoxical radio glow, one truth becomes overwhelmingly clear. The Crab Nebula is far more than a beautiful cosmic corpse. It is a dynamic, evolving, and profoundly mysterious universe in miniature. Every single one of these baffling behaviors, the gamma-ray superflares, the missing mass, the chaotic magnetic fields, the impossible particles, is not a flaw in our understanding but a frontier. Each one represents a crack in the foundation of known physics, and through those cracks we glimpse the brilliant light of discoveries yet to be made. This isn't just an academic exercise. Unraveling why the pulsar nulls its radio pulses or how its jet maintains its perfect structure forces us to rewrite the textbooks on quantum mechanics, plasma physics, and general relativity. The nebula is a natural laboratory operating at energy scales and under conditions we could never hope to recreate on Earth. Its mysteries are direct questions from the universe itself, challenging us to think bigger, dig deeper, and venture beyond the comfortable confines of our current models. The greatest takeaway is that no object in space, no matter how well studied, is ever fully understood. There are always deeper layers, stranger twists, and more profound secrets waiting for the next generation of telescopes and the next brilliant mind to uncover. Now we turn to you. Which of these 30 phenomena captured your imagination the most? Was it the haunting illusion of matter moving faster than light, or the silent, ghostly rings that appear in the radio silence? Perhaps it was the chilling possibility that dark matter annihilation is powering the glow, or the simple, profound mystery of where the rest of the star's mass went. Share your thoughts in the comments below. We'd love to hear which cosmic puzzle fascinates you and why. The story of the Crab Nebula is a powerful reminder that the universe is not just stranger than we imagine, but stranger than we can imagine. It encourages us to stay curious, to keep looking up, and to never stop asking why. So the next time you gaze at the night sky, remember that every point of light holds endless wonders, and that the greatest discoveries often begin with a single, baffling observation. Thank you for joining us on this incredible journey to the heart of a cosmic mystery.